In this lesson, we're going to solve exponential equations. And there are actually two more lessons left in this unit. We're going to solve exponential equations and we're going to solve logarithmic equations. So the first kind of exponential equations we're going to solve is basically a power on the left side and a power on the right side. So something that looks like this. So 4 to the power of x equals 2 to the power of 4. And I'm not going to say this equation is hard to solve. In fact, I think most of you can solve this equation. But this question would be much easier if the bases of the two powers are exactly the same. Like, for example, compare this equation with this equation. 4 to the power of x equals 4 squared. I would argue it's much easier to solve than the first equation I have here. Now, why is that the case? Because if the powers are equal and the bases are the same, we can actually just solve for x by equating the two exponents. So x is equal to 2 in this case. Now you might be wondering, is that safe to assume? Is x really equal to 2? Is there another value we can sub in to make left side equals right side? So what I'm going to do is I'm going to show you another equation. So if 3 to the power of x equals 3 cubed. So I'm going to argue that x can only be equal to 3 to solve this equation. Now, how can I prove this argument to be correct? Well, you need to think about 3 cubed, okay? So 3 cubed is 27. 3 cubed is 27. Now, interestingly enough, if you have a power with a base of 3, the only way to make 27 is if your exponent is 3. Okay? If you have a power with a base of 3, the only way to make a value of 27 is 3. And that's the relationship with this power. It has a 1-to-1 correspondence, which means if you're going to generate a value, there can only be one exponent to do so, okay, if the base of the power is 3. So, I don't know, let's say you want a value of 81. You can only have an exponent of 4 and a base of 3. Okay, 3 to the power of anything else will not give you 81. And that makes sense because if you think about the exponential function, okay, each x value will give you a unique y value. And each y value will give you a unique x value. Okay, so I know that's a little hard to conceptualize, but each y value will give you a unique x value, which means it's a 1-to-1 function. So that means it's safe to assume, or not assume, but safe to say that x is equal to 3. And there's no other value of x which will solve this equation. Now there are some things that's going to break what I just said and render it incorrect. So for example, if I have 1 to the x equals 1 to the 6, okay, it would not be safe to say x is equal to 6, because if x were to be 5, let's say, 1 to the power of 5 is 1 and 1 to the power of 6 is 1, so x is not 6. Now why did that fall apart? Because the base is 1. If you have a base of 1, what does your graph look like? It could be 1 to the x, which is a horizontal line. So when we solve these exponential equations, the bases that we have will be positive and not equal to 1, okay? We're going to keep the same restriction on the base as we did before. Okay, so all I'm trying to say here is if you have two powers, having a common base would be a great idea, because if the bases are common, you can set the exponents equal to each other. Okay, so here I have a base of 4 and a base of 2. Let's change them both to a base of 2. I could change 2 to be square root of 4, but it's much easier to say 4 to be 2 squared. Okay, grade 9, power of power. When I have a power of power, I'm going to multiply the exponents. So since bases are the same, therefore I'm going to set the exponents equal to each other. So that's going to be x is equal to -3. I did say solve and check, but you know what? You're going to check on your own time. I assure you, -3 is correct. But it's always a good idea to check your answers, especially when you're solving an equation. Why not? So for b, I have a base of 9 and a base of 27, so let's express both as a base of 3. So power to power, power to power, multiply the exponents. Grade 9 exponent laws. They're going to come really handy in this lesson. So bases are the same. So 6x plus 2 equals 3x. So if you do the math, x is equal to -2 over 3. Because you get 3x equals -2. Yep. Okay, let's do this one. So for C, I don't have a power on each side. I have actually 2 powers on the left-hand side. So to solve this equation, you have to think back to grade 9. Okay, in grade 9, you learn a bunch of exponent laws. One of them says that if you multiply 2 powers with the same base, you add the exponents. So in grade 9, usually you would simplify into a single power. Okay, you express a product of 2 powers with the same base as a single power. But what you want to do here is you want to reverse that logic. You actually want to break this power into a product of 2 powers. So 3 to the power of x plus 2 is 3 to the x times 3 squared. Now why would you want to do that? I want to express it as a product of 2 powers because 3 to the x now becomes a common factor. Okay, I'll write 3 squared. Okay, so now you can see it's much easier to solve for x now. So 3 squared minus 1 is 8. So 216 over 8 is 27. Okay, there you go. So if you're struggling to solve for x here, you need to work on your powers because you should really know 3 cubed is 27. But if you're really struggling, what you can do is change it to logarithmic form because that will solve for x. Usually I wouldn't do this, but that's how you would do this if you were to use logarithms to solve for x. But you should really know 3 cubed is 27. Okay? Logarithmic form, good friend. It's going to help you solve for your variables here. Okay, same strategy. So subtracting by 1, you can say it's 5 times 5 to the power of -1. I'll factor out 5 to the x. So this is 1/5 minus 1, which is -4/5. Divide both sides by -4/5. You get 1. 5 to the x equals 0. You could change it to logarithmic form if you want, but you should really know x equals 0. 0 exponent will give you a value of 1. All right. So let's keep solving exponential equations. So you might not see what I see here, but I'm really hoping you can say that you see quadratic, okay? When you see this equation, I'm hoping you think quadratic. So 16 is 4 squared. Hopefully you see it. Now this is a power, so you can multiply exponents, so you can actually rearrange this. So it's 4 to the x squared. Okay, and if you still have trouble seeing the quadratic, you can say let z equals 4 to the x. So if that's the case, you should really be able to see the quadratic. So z squared minus 20z plus 64 equals 0. So z minus 16, z minus 4 equals 0. It's a simple trinomial, right? Two numbers that multiply to 64 and add to -20. -16 and -4. So using the zero product property, so z is equal to 16 or z is equal to 4. To be honest with you, I couldn't care less what z is. What I want to do is, or what I want to know is what x is. So I'm going to replace z with 4 to the x. So you could change the logarithmic form, but hopefully you know 4 squared is 16, 4 to the power 1 is 4. You should really check on your own time. Make sure 2 and 1 are correct, but I can assure you they are. Alright, so what if you can't create a common base? So for example, I have a power with a base of 4 and a power with a base of 3. Now you can actually create a common base here. It is doable, but it's actually not a very good strategy because it'll be very time consuming to solve this equation. So what the textbook does is they take the logarithm of both sides, okay? They take the logarithm of base 10 to both sides. And I'm going to first start off by saying the textbook does it this way, and I highly don't recommend it, but I'll show it to you anyways. So logarithm of the left side, logarithm of the right side. You could choose any base. You could choose actually a base of 4 and a base of 3, and that might make it a little faster, but I'll just choose base 10 because that's what the textbook does. And after that, you can use the power law of logarithms. And then we're going to expand here. And then I'm going to bring the x terms to the left side. And the other terms, keep it to the right side. And guess what? I'm going to factor out x. Alright, and then let's solve for x. I'm running out of room, so I'm just going to write it up here. So log 4 plus 2 log 3 all over 2 log 4 minus log 3. Okay, so that's what the textbook says, and I really don't like this answer actually, because why bother learning logarithm laws if you're not going to make use of them? Because you can express this answer as a single logarithm. So I really don't like this chunky answer. I mean, it's correct, but at the same time, I don't like the way it looks. So what I'm going to do is I'm going to clean that up. So this becomes log 4 plus log 9, because 3 squared is 9, using the power law of logarithms. And 2 log 4 is log 16, because it's 4 squared. Once again, power law of logarithm. In the numerator, I'm going to use the product law of logarithms, and the denominator, I'm going to use the quotient law of logarithms. So log 4 plus log 9 is 4 times 9 is 36, and this will be log 16 over 3. And now I'm going to express a single logarithm because I can use the change of base formula. Oh, that was a lot of work. So I will show you the shortcut. And by the way, your answer may look different. So there's logarithms that may look different, but numerically they are the same. So just like if your answer doesn't match up with the answer key, it might not be incorrect. It might not be wrong. You just have to check the numerical value. Now, if numerically they're different, then you're probably wrong. Okay, but I can show you a logarithm that looks entirely different and is actually the exact same value. So my way of doing it is to really make use of your exponent laws from grade 9. What I'm going to do is I'm going to break apart this exponent. Okay, so take your time and try to see how I broke it apart. So this plus means I'm going to use the product law of exponents. Okay, I'm going to express it as a product of two powers with the same base of 7 in this case. Now 7 to the power of 2x is exactly the same as 7 to the power of 2 raised to the power of x, because there's a power of power, and that means you multiply exponents. So 7 squared raised to the power of x is the same as 7 to the power of 2x. Okay, you might be wondering why I'm doing that, but it will make sense in a second. Now 4 to the power of x, 4 to the power of x minus 2, I can write it like this. Because in grade 9 we said that if you subtract exponents, you're basically dividing powers with the same base, okay? So I'm going to clean that up a little. So my goal is to solve for x. So I see x on the left and right side, so I'm going to simply set it to, I don't know, let's say the right side. Okay, so I'm going to multiply both sides by 16 and divide both sides by 49 to the power of x. So I get 4x over 49 to the power of x. Okay, so 70 plus 42 would be 112. So 112 is equal to, okay, so this is what I'm going to do. This is also a grade 9 exponent law. So 4 to the power of x over 49 to the power of x is equal to 4 over 49 all to the power of x. That's something you learn in grade 9, okay? Let's go over it. A to the n over b to the n is a over b to the n. So hopefully this step makes perfect sense to you. Just refresh your memory from grade 9. And now I'm going to one more step and I'm done. Logarithmic form. And I am done. Much easier than what we did for part A. Okay, let's compare and contrast that. Whoa, a lot less steps, much more simpler. And when you do what you do, like if you do what the textbook suggests, it's very easy to make a careless algebraic mistake. So I highly recommend you to really look at what I did for part B and try to understand the steps. It's really a bunch of grade 9 steps, to be honest with you. So I'm going to do D before I do C actually, because A, B, and D are actually, to me, exactly the same question. So I'm going to use my shortcut, but this time I'm going to speed it up a little. I won't, show all the steps because that was really unnecessary. So 2 to the power of 3x, I'm going to write 2 cubed to the power of x. 3 to the power of 5x minus 1, we'll write as 3 to the power of 5 to the power of x over 3 to the power of 1. So I'm going to do 3, and then I'm going to bring that terms with x on the right hand side. 3 to the 5 is 243. 2 cubed is 8. And then logarithmic form, and I'm done. So the hardest part, I would argue, is the first step. You're using your grade 9 exponent laws and really decomposing that power. Because in grade 9, you actually go the other way around, but now you're asked to go backwards because you really want to unlock and solve for x. So you want to break down that power. Anyways, if you're more comfortable doing it the textbook way, sure, go ahead. It makes no difference to me. But I do want to give you a nicer way of doing it, or what I believe to be nicer. All right, so let's try 3C. I would argue 3C is exactly like 1C we did on the first page. You just have to break apart this power as a product of two powers with a base of 8. So I'm going to factor out 8 to the x. 8 squared is 64. 8 cubed is 512. Yeah, 512. So then we're going to do 64 minus 512. And we're going to take -5 and divide by that. Just make my calculator, double check my calculation. Okay, so it's going to be 5 over 448. Logarithmic form, done. Okay, one last page to go. So we have have 2 to the x equals 2 to the power of negative x equals 4. So I'm going to write this negative exponent as 1 over 2 to the x. Okay, so what we're going to do is we're going to multiply both sides by 2 to the x. And why might you want to do that? Because I'm hoping you see that once I multiply both sides by 2 to the x, you have your quadratic, right? You have your quadratic here. So 2 to the x all squared minus 4, 2 to the x minus 1, set that equal to 0. Unfortunately, I can already see that it's not factorable. So you have z squared minus 4z minus 1 equals 0. So since it's not factorable, we're going to use the quadratic formula. Oops, I already wrote the let statement for z. So, quadratic formula, negative b plus or minus b squared minus 4ac all over 2a. So 16 plus 4 is 20. You can clean that up a little because root 20 is 2 root 5. So you can get 2 plus or minus root 5. Okay, so since z is 2 to the x, you have 2 plus root 5, or 2 to the x equals 2 minus root 5. And I'm going to focus on 2 to the x equals 2 minus root 5, because 2 to the x equals 2 minus root 5 has no solutions, okay? Because I know that 2 to the x must be greater than 0. 2 to the x must be greater than 0. You can think of the exponential function graph, you can think of just your knowledge of powers, but 2 to the x must be greater than 0. And I know 2 minus root 5 is negative, because root 5 is greater than 2. Because root 4 is 2, so root 5 must be greater than 2. So since this is negative, I'm not going to get any roots here, okay? So I'm going to ignore this equation. I know I'm not going to get an answer from that equation. So I'm going to focus on this. 2 to the x equals 2 plus root 5. Beautiful. Space 2 plus root 5. Perfect answer. Exact answer can't be any better. Now in the homework sheets, they ask you to evaluate this. To be honest with you, I love exact answers, and to me there's absolutely no reason for you to approximate that value. I guess the only reason to is just see if you can do it using a calculator, but the exact answer is really superior. Okay, 2 more to go. So example 5 is a classic half-life question that you did in grade 11. So just a reminder, this is the formula we use for half-life in grade 11. The amount left is equal to the original amount times half to the power of t over h. So t is the time that has passed and h is the half-life. So remember, half-life is the amount of time that it takes for you to lose half of your original amount. So we don't know the half-life of thorium-233, and we're going to solve for that. So you have 17 grams after 5 minutes. You start off with 20. Oops. And the 5 minutes. Okay, so let's solve for h. So log base half of 17 over 20 is 5 over h. And then just rearrange. There you go. And the units for half-life is in minutes. So therefore, the half-life is how many minutes? You can probably find the approximate value, but I'm not very interested. I will show you in the next part, because I will find the approximate time it will take to decay to 1 milligram. Okay, so since I have the half-life, I can do this question. So you start off with 20 milligrams. How long will it take to drop to 1 milligram? 1 milligram. Okay, so logarithmic form. So if I didn't know the half-life, I couldn't tell you how long it will take to decay to 1 milligram, which makes sense. If I don't know the half-life, how am I going to tell you the time it takes it to decay to 1 milligram? But luckily I do have it, so I'm going to find the approximate value. So I'm going to calculate the half-life for you now. So log of 17 over 20 divided by log half. Okay, that's in the denominator, so 5 over that. That's my half-life, about 21.3 minutes. Take that and multiply by this logarithm here, so which is log 1 over 20 divided by log 0.5. So we're looking at 92 minutes, about 92.2 minutes. So it will take approximately 92.2 minutes to decay to 1 milligram. Okay, so that's the last question for solving exponential equations. Hopefully that wasn't too bad.